Welcome back. This is the second segment of section 1.1. And as you'll recall, we were just starting to get into some things about angles. We haven't really touched on anything yet that is beyond what you might see in a basic geometry class. The next step here is that we're going to start trying to come up with a way to turn these shapes. I mean, angles are just kind of a weird shape that exists in space, and try to come up with a way to actually measure them so that once we have a number attached to them, we can then use, we can, in some sense, we have trigonometric functions that take an input, which is the size, if you will, of the angle, and then they have an output, which is a real number. So that's kind of where we're headed. We're still trying to define a few words. So hopefully you all are caught up with this, and this doesn't seem overwhelming just yet, which it shouldn't. But just in the meantime, just be real cognizant of the terms that are being used as they're defined, and then we can go back to maybe eventually we can go back to some application. So recall we had talked about the definition of an angle, which is the union of two rays, and we gave some different notation for how that might be represented in a geometry class. Sometimes people use something that's a little more elaborate than this little half triangle, but this is sufficient for anything we do. Okay, so here's sort of a general statement that is without proof. All angles have a measure. Okay, and that's just a statement about how we're going to approach trigonometry. What does that mean? It means that there is a number that's associated with the sort of size of the angle. And I'll try to be a little more precise about how we come up with that measurement right away. So beginning with one side of the angle. Recall the sides are basically another word for rays. And we're going to be able to distinguish these. I'm going to call this called the initial side. The measure is determined either clockwise or counterclockwise I'm going to kind of run out of space here. So just continuing right along here. Sorry, I missed a word here. It's determined by either clockwise or counterclockwise rotation of the initial side to the so-called terminal side. Okay, so what is this saying? It's saying, well, basically every angle, no matter how you construct it, is these two rays, and at some point you pick one of them, and you call that the initial side, and then you look at how far or how much rotation is required to get from the initial side to the other side, which is called the terminal side. Now you got to bear in mind that it is certainly possible to go around more than one time. Like you could have a complete rotation and come back. That's not really applicable to things like triangles and whatnot, but it certainly is relevant if you were talking about the rotation of a wheel or some kind of a circular type object. So the number of windings, the number of times that you go around should make for a different measure, which is kind of an interesting idea that you don't have in geometry. So we want to talk about, now that we have sort of a direction of rotation, we're going to assign an SIGN to what that rotation means. So clockwise rotation means negative measure. So you can, in some sense, have negative angles. Counterclockwise, on the other hand, is positive. One other sort of statement: rotation can include one or more complete rotations that was kind of a statement that you can go around more than once, so to speak. Okay, so before we get in, maybe I should state this about the actual, like the units that we're going to use first. So if we talk, we're continuing our discussion about the measurement of an angle. So most commonly, and this is probably what you're most familiar with, most commonly angles are measured in degrees. A complete rotation measures plus or minus 360 degrees. And note this symbol that we're using. I know that this is very common for everybody, should recognize what this is, but one thing that I notice is that students often forget about the unit when they're doing some of their homework, especially here at the very beginning. So just be cognizant that things that have units need to have units. This degree measure, 1 degree is measured as 1/360th of a complete circle, but it does have a unit, and later on in the semester we'll try to move to something that's unitless. So, but please do not forget to put those kinds of symbols in place when they're appropriate. So maybe just if I take a quick minute here and kind of summarize what these two ideas are talking about. So let's just start with an angle, and I'll kind of do it here in the bottom of this page. But let's just say here's our angle, right? We don't actually need, let's just call it angle A. Now, depending on which side you pick as the initial side, right? I mean, it's natural to want this one to be the initial side, but this could just as easily be the initial side. And I'd say, you know, I'm going to appeal to your knowledge of sizes of triangles. This looks like maybe about a 45-degree angle in here. Well, if this is the initial side and you rotate clockwise to the terminal side, then the measure of that angle is actually negative 45 degrees, right? On the other hand, if again, this is the initial side and your rotation is all the way around in a counterclockwise fashion to the terminal side, this would actually be a measure of positive 315 degrees. In some sense, those measurements are different, but at the same time, there's some similarity to them. The shape of the angle is exactly the same. And so we're going to find that these trigonometric functions act on measures of angles, and it doesn't really matter if you go around only partially, if you go around a couple times, but it does matter this direction, because if you change the identity so that this is now the initial side and this is the terminal side, then you end up with different measures that are relevant. So in this case, if this is the initial side and this one's the terminal side, then that measure of that angle is actually positive 45 degrees. On the other hand, if you started here and rotated in a clockwise fashion, it would actually be negative 315. Those SIGNs really matter. The number of rotations is not quite so important. But anyways, that's just sort of an aside to kind of illustrate what's going on here. Because in geometry, it doesn't make any difference. But for trigonometric purposes, the measure has to have a precise way that we can calculate it, or measure it, or state it, or whatever else, because we're going to use the size to then produce some very interesting functions. Okay, so on here, we're going to introduce some additional notation. So commonly, and you're going to find as you take a trigonometry class, you're going to get proficient at the use of Greek letters. I think this is actually page 4. Sorry. Okay. So, and this is almost exclusively when we're talking about degree measurements, but we often use Greek letters to represent the measure of an angle. And I'm just going to list the most common ones. The most common and sort of the default one is this, and these are all lowercase Greek letters. You can use uppercase, but that's kind of a strange thing that people don't typically do. So you have theta. I'm going to try to spell its Romanized version. So theta is very, very common. This one is, I guess I've heard it 2 different ways: phi, phi, maybe faux fum. But you'll have some people disagree on what the name of this is, but I think it's actually supposed to be phi. Another one that's very common is alpha. Also, we have beta. And sometimes you'll see gamma. Another one that's very common is delta. So you don't necessarily need to know the names of these things, but here's sort of the critical part to take away from this. As you're reading mathematical notation in text, there are visual cues that are often embedded in that text so that people have some kind of an idea of what it is that they're looking at. It is very common, for example, to use X's and Y's to represent coordinates on a coordinate axis, almost to the point where you just automatically understand that an x-axis is generally represented horizontally and a y-axis is represented vertically. There's no reason why you have to do that. You could call it just as easily, axis U, V, W, or some other symbol, some letter, but it has been adopted by the mathematical community that these kinds of symbols are sort of representative of these sorts of things. You see that when you're talking about like algebra, you talk about the coefficients on a quadratic equation or quadratic function. It's always ax squared plus bx plus c, and why a, b, and c? Well, a, b, and c have historically been used to represent constants that maybe have an unknown value, so that you can create formulas for equations like the quadratic equation. The quadratic formula, which is, x is equal to negative b, blah, 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 blah. So this is the visual cue. If you see things that look like this, in almost every case, at least sort of initially, I mean, granted, some authors will use different things, but if you see this, this should be the visual cue that you're probably talking about something that's an angle. And that's kind of an important aspect. It's not just a random variable. It's not some kind of weird function or weird notation. It's actually a letter, even though it's Greek, that's being used to represent the measure of an angle. Okay, so for now, we're going to focus on just a certain types of angles. So for now, let's consider angles. Let's say positive angles. Add that in there. Positive angles with measures between 0 degrees and 180 degrees. Now that's basically remember the complete rotation is 360 degrees, so this is just half a rotation, and this is no rotation at all. In geometry, there's nothing to describe a 0 degree angle. A 0 degree angle doesn't really exist in geometry. It's actually a ray. So it doesn't really have a name. We're going to focus on some things involving triangles, and any real triangle has angles that measure, or at least the internal or the interior angle measures somewhere between 0 and 180 degrees. So that's where the terms become relevant. So an angle, let's consider positive angles, and so say angle with measure theta. Okay, so if theta is between 0 degrees and 90 degrees, this is what's called an acute angle. And this is a term that's used especially with triangles, because there's some relationships between acute angles and other kinds. If it's equal to 90 degrees, this is called a right angle. If it's strictly between 90 and 180, we call this an obtuse angle. And if it is equal to 180 degrees, this is sometimes called a straight angle. You'll hear different terms for this last one, but straight angle seems to be what the textbook likes. Again, though, a straight angle in geometry is not an angle. It's actually a line, right? Even though there's sort of a point in the middle that represents the vertex, it is a line if it's 180 degrees. So you have sort of a problem at 0, where 0 degrees in a geometric sense isn't really an angle, it's a ray, and 180 degrees is actually a line. But we use these terms enough that we'll just kind of work with them. Okay, so what are we going to do with this stuff? We've still got a couple more terms that we want to define that have to do with the relationships between angles. And they have to do with some of these terms that you're probably a little bit familiar with, but I want to remind you because we use them all the time. So let's say given two angles with positive measure, and we'll say theta and phi. So what I mean by positive measure means that it's, I mean, I guess they could be actually equal to 0, but it doesn't make a whole lot of sense in this context. But these are the terms we're wanting, and these should be very familiar. We say, say the two angles, got a couple different things we want to define, are complementary Now, this word is not like compliment, like yay, congratulations, because that word actually has this is an I instead of an E. So this complementary is in the sense that it complements or adds to or makes whole, I guess is maybe a way to think about that. So the two angles are said to be complementary, like they're complementary to each other. It doesn't, you're not like saying, well, one is the complement of, but that can make sense too, if phi plus theta is equal to a right angle or equal to 90 degrees. So complementary, 90 degrees. Supplementary, which is another term that's used quite frequently, if they're equal, their sum is equal to 180. So if they add up to, say, a straight angle. Now there is one other one that comes up, oh my gosh, we won't see this for a very, very long time, and it's not even in the textbook, but I'll go ahead and throw it down here just so you've got sort of the complete package here. It's what's called an explementary angle if they add up to a complete revolution. 360 degrees, okay? So explementary, don't worry about that too much. These are the two you really need to focus on, complementary and supplementary. You have to have those nailed down, because what I've seen students do over and over and over again is that they get these two confused and they have, well, is it 90 or is it 180? It's really just a pretty simple idea, and you have to be able to make this connection, because here's the geometry words and here's the algebra that's associated with it. We'll be focusing more on the algebra. So one of a sort of a simple problem associated with this, and I'm going to do this problem, and then we're probably going to finish this segment up. So for example, let's say find the measure of each angle. Or maybe measure of these angles. So I'm going to draw, let me draw one here. It's not to scale, and drawings are never to scale, trust me. But let's use this little notation. I'm sure from geometry this is familiar. That means that this is a right angle. And this, let's say phi equal to 5x minus 2 and theta equal to 4x plus 2. So what this question is asking us to do is to find the measure of theta and phi by using this algebraic sort of problem setup, okay? So since these angles are complementary, and usually you don't have the picture, it's just that two complementary angles have a measure of 4x plus 2 and 5x minus 2 for some value x. Find the measure of each angle. That's another way of saying sort of the same thing. But the problem that I often find is that students want to find x and then they forget to come back and calculate what the actual angles are. So starting with the fact that they're complementary, we know that the sum of these two angles, phi plus theta, equals 90 degrees. Okay? So now substituting what the values are given for these, we have 5x minus 2 plus 4x plus 2 equals 90 degrees. So when you simplify the left-hand side, you have 9x is equal to 90 degrees, or x is equal to 10 degrees. Okay, so a lot of students will stop here and say, I found x, so I'm done. And that's not what the question's asking. The question's actually asking for the measure. So going back then, we have that theta is equal to 4 times 10 degrees plus 2 degrees. Probably should have been very careful and put that unit in there. I can correct that, 2 degrees. So 4 times 10 degrees plus 2, which is going to be 42 degrees, and phi, which is 5 times 10 degrees minus 2 degrees, is equal to 48. And we can check, I mean, this is a very simple problem, but we can check and just make sure that they add up to 90 degrees. Now, where people get kind of thrown off is when they forget the difference between complementary and supplementary, and then they try to make this equal to 180, you end up with a different answer, and blah, 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 blah. Okay, let's try one more, maybe one that involves supplementary angle, and I won't actually draw the picture for you. I'll write it in a way that is probably a little bit more designed to make sure that you kind of have nailed this down. So this is now page 6. Okay, so another example. Suppose two angles our supplementary. With measure eight x plus 9 and 6x plus 3, respectively, for some, and I'm going to put the degrees in there, sorry, blew it last time, for some value of x, find the measure of the two angles. So we are trying to be very formal here. So in order to start using a symbol, I might want to define what it is. So since these aren't actually given some kind of representation, I'm going to actually make that first thing. So we'll say let theta equal 8x plus 9 degrees and phi equals 6x plus 3 degrees, okay? Since they're supplementary, we know theta plus phi is equal to 180 degrees. Substitution then yields 8x plus 9 degrees plus 6x plus 3 degrees equal to 180 degrees. And to simplify this algebraically, then we have 14x is plus 12 degrees equal to 180 degrees. Now this is simple algebra, but for whatever reason, people kind of mess this up sometimes. Just be very thorough. So 14x is equal to 168 degrees. And if I did the arithmetic correct, I think that means that x equals 12 degrees. Now, a lot of people will just stop there, which you shouldn't. You have to go back and substitute them into the original arguments. So theta is equal to 8 times 12 degrees plus 9 degrees, which is, well, 8 times 12 is 96. So we're talking about 105. And phi is equal to 6 times 12 degrees plus 3. 6 times 12 is 72. Add 3 to it, we have 75. And now we can check to make sure that these add up to 180 degrees, which they do. So this would be sort of our first angle and our second angle. And that would solve the problem for us. Different sorts of notation pop up in the book. I'm not really too concerned about sets and that sort of thing. Anyway, so we've gotten a little bit long here. This is it for this segment. We've still got a little bit more to cover in section 1.1. We want to talk about some other kinds of measures and some different definitions of triangles, angles. So I will see you back